Hello, welcome to another graduate classical mechanics video of Dr. Vives. Last time we looked at the orbit equations leading to Kepler's three laws of motion, and the method we used was very close to what Newton himself would have used. Now, this problem was one of the hot topics of the 18th and 19th centuries. People were trying to understand the deep reasons behind the orbital motion. For example, why is the motion planar? Is there more to that meets the eye? So today's lecture is about the Laplace-Runge-Lenz vector, which was discovered as one of the central aspects of symmetry in the Kepler problem. So let's start with some history. This vector was actually first discovered by Jacob Hermann, who was a student of Johann Bernoulli. This is the John Bernoulli, who gave such a beautiful solution to the brachistochrone problem. Well, his pupil made the following argument, which I'm going to outline. The force of gravity between two objects is given by Newton's law as follows. Which is the familiar inverse square law times r hat, where let's define a few terms. R hat is the vector that points from it's a reduced or relative vector I sometimes like to call it the reduced mass relative vector. It's a vector that points from object 2 to object 1, object 2 being the sun, and object 1 being the planet. So it should be thought of as the sun to planet vector. The reduced mass, mu, is given as m1, m2 over m1 plus m2. I introduced this last time in the context of the two-body problem. We also defined a total mass m, which is the sum of the two masses, for example, the sun and the earth. So let's just keep all this in the back burner. I'm also going to define a new constant, k, unrelated to any uses of k in the previous video. And this is g Newton times the total mass m. We'll soon see this quantity k coming up quite frequently. So associated to this force, because the force is the negative derivative of the potential energy, where capital V stands for the potential energy, we have the potential energy of the two-body problem, and that is negative Gn m1 m2 divided by r. Quickly verify, if I take d by dr, I get 1 over r squared with a negative sign, which cancels this negative sign, but because of that negative sign, it comes back. So that's what we have. Now, let's write Newton's second law in the reduced mass scenario. Newton's second law looks like mass, which is mu, times the acceleration, d2r over dt squared, is equal to the force. And the force is given by that. Let me write this. Times the unit vector r. Now, mu has got m1, m2 in the numerator. So that m1, m2 and this m1, m2 cancels out. In the denominator, I have capital M, which is m1 plus m2, which goes upstairs. So this leads to d2r over dt squared equals negative g sub n times capital M over r squared r hat. And now g sub Newton times capital M is our new constant k. It is this quantity that Jacob Hermann was interested in working with. Now, he did some vector algebra and found some very interesting things about this quantity. We're going to replicate his footsteps. So r cross, what if I take r cross dr by d2r by dt squared? Well, because r cross r hat is 0, this is going to be 0. But it's also equal to this quantity to the left is also equal to d by dt of r cross dr by dt. Let's quickly see why that is. If I expand this out, I'm going to get two terms by the Leibniz rule. I'm going to get dr by dt cross dr by dt, which of course is 0 because the vector cross itself is always 0. And then I'm going to get another term, which is r cross, the derivative of the other thing, which is d2r over dt squared. So as claimed, I can always write the left-hand side as d by dt of this, since this term is 0. So what I have shown is, or what rather Jacob Hermann showed, was that this quantity is equal to 0. So he, probably after his last name, because his last name is Hermann, called this the vector H. The Hermann vector, if you like. That's r cross dr by dt. This has to be a constant because the derivative of this vector is 0. Now, you can actually find a geometric interpretation for this constant. It is just twice the area vector, because the area vector in polar coordinates is 1/2 r cross the velocity v. So a prime. Let's just look at this quickly. Here's your orbit. The sun is in the middle. That's your object 2. The Earth is object 1. So that is the radius vector r. The vector we call a prime is going to be perpendicular to the orbit. And its magnitude is given by 1/2 r cross v. The velocity vector, meanwhile, is tangential to the orbit. So you can see that 1/2 r cross v is just going to be the area of that little triangle. And if you keep summing it up, you get the entire area of the ellipse. So this gives you the instantaneous area vector at any given time. So that's just a little proof. This is sometimes called the aerial velocity vector. Now, the Hermann vector has got an interesting property, and that is the following. R dot H is 0. The reason for this is obvious because H itself is R cross dr by dt. In other words, it's R cross the velocity. So if it's R cross the velocity, it must be some vector that's perpendicular to both r and v. In other words, the Hermann vector itself must be somewhere over here. All right. In fact, it is actually twice as big as the area vector. I've just written there that H is equal to 2a prime, so I wrote it as half as big. I should have written this twice as big, but I realized that if I did that, I'll run up to there. Let me do that for the sake of accuracy. That's your Hermann vector. It's twice the size of the area vector. So looking pretty interesting. So r dot h is obviously 0 because h is perpendicular to the plane of both r and dr by dt, or the velocity. So r dot h must be 0. That's obvious. This immediately gives us Kepler's first law. This tells you that r must be perpendicular to h, or that since h is a fixed vector because it doesn't change with time, this tells you that r is planar. So in this manner, he got Kepler's first law, which I called K11 part 1 last time. From here to Kepler's second law is the next tantalizing step, which Jacob Hermann carried out. So really beautiful analysis. Let's do that next. Now remember that this r hat vector is proxy for the full vector r divided by its magnitude. So what I'm going to do now is find out what will happen if I cross the Hermann vector with the acceleration vector. Why do something like that? Let's just be patient and proceed to see what happens. Well, because d2r by dt squared is equal to negative k over r squared r hat, which in turn, because of r hat being r over r, is negative k over r cubed r vector, I'm going to use that in here. So that's going to be negative k over r cubed r vector cross the Hermann, which is r cross dr by dt. Now that's a triple cross product. Immediately your alarm bell should go off because you have a very famous identity known as the Lagrange triple cross product identity. In one of the earlier videos, we looked at this identity. So I'll just remind you of it. It says that when you have A cross B cross C, this is none other than the middle vector times the dot product of the other two vectors minus the last vector times the dot product of the other two vectors. So let's use that identity. I'm going to take negative k over r cubed outside. So the middle vector is r times the dot product of these two. Minus the vector c, which is dr by dt, times the dot product of r and r, which is just r squared. Now what I will do is I'll pull negative k over r cubed inside. If I do that, the second term will lose its minus sign because two negatives make a positive. There's an r cubed and an r squared, so I get 1 over r. Let me write the second term first. K I will leave outside. So I get 1 over r times dr by dt from the second term. What happens to the first term? For the first term, I'll do the following. I'll take one factor of r for this r vector inside the dot product. So when I do r divided by r, I get r hat. So I'll do that one. Meanwhile, I have r and one factor of r squared left over. I'll leave that outside. So again, what I've done is I've taken one factor of r and made this a unit vector while I've kept everything else the same. So let's look at this. That's going to be k times 1 over r dr by dt. Now let's look at the second term. When I do the dr by dt is the total velocity. When I do r hat dot that, I just get the r component of the velocity. So that's going to be r over r squared times dr by dt. Now, Hermann realized that this was just d by dt of something, and that is k times d by dt of r over r. In other words, it's the total derivative, time derivative of r hat. Let's see how that is. If I take d by dt of this, the first term will give me 1 over r dr by dt. That's this term. Then I have to leave this alone and differentiate the denominator. So that gives me negative 1 over r squared dr by dt. Done. So by a simple application of things like chain rule and vector identities, Hermann got to this point. All right, but this is not where he wanted to go. Then he did the following. D by dt, what happens when you have d by dt of just the velocity vector, dr by dt, also known as v, cross the Hermann vector. Let's see what this looks like. V cross h should be another vector that's somewhere here on the plane of the orbit itself. But let's find out what it is. When you apply Leibniz's rule, I differentiate the first term. And then I have the dr by dt times the derivative of the second term. But the Hermann vector is constant. It's equal to 2 times the area vector. Therefore, dh by dt is 0. So this entire term just gives me 0. Which means that what I've actually calculated there is d by dt of this. Let me write the left-hand side now as d by dt of velocity cross Hermann. So therefore, I'm getting d by dt, dr by dt cross h is equal to k times d by dt r over r. Now this is almost looking staggering because there's a completely new symmetry of the Kepler problem that nobody had discovered before Hermann. And if I take the d by dt to the left side of everything to the left side, I'm going to get dr by dt cross h minus k r over r equals 0. Later on, it was found that two other scientists, Laplace and Runge, and also a German scientist called Lenz, had discovered the same thing. So rather than, even though Hermann also, when he was a student, worked out these things, because students never really get fully credited, the vector whose magnitude, the time rate of change is equal to 0 is now called the Laplace-Runge-Lenz vector. So let me define that vector. So the vector A, which is everything inside this flower bracket, this is the famous Laplace-Runge-Lenz vector. Laplace was a very famous scientist who made a lot of contributions to celestial mechanics and, of course, the mathematical physics. Terms like Laplacian, Laplace operator are named after him. Runge made many contributions to analysis also. For example, the Runge-Kutta method for doing approximations of differential equations is well known to most students. And Lenz, he's the same Lenz who had some contributions to electrodynamics around the same time. Everybody knows what Lenz's law is from basic physics. He's the same Lenz. So that's the vector. And as I pointed out, Hermann was already on it. So Hermann calculated its magnitude in the year 1710. And his advisor got really interested in it when Hermann showed it to him. So Johann Bernoulli found its direction 3 years later. Now, when you look at things like this, direction 3 years later, you wonder what's going on. Why did it take 3 years to go from there to there? These were times when this was a hot topic. Things were happening, and it always looks strange from a historical perspective, because today I'll be giving you the direction in 5 minutes. So once you are up to here, the equation of orbit, which we took such a long time and so much difficulty in getting, comes out in 2 steps. So let's look at the equation of orbit next. For this, let's look at the square of the Hermann vector. Well, that's going to be h dot r cross dr by dt, because remember, the Hermann vector is just the cross product of the radius vector and the velocity vector. All right. So I can write it as r cross dr by dt dot r cross dr by dt, but it looks confusing, and it's good to have things only one at a time. Now, there is a very famous property of the triple scalar product. This is called the triple scalar product because it's got a dot product and a cross product together. So the triple scalar product has got an important property known as associativity. It says the following: if I have A dot B cross C, then I can interchange cyclically the order of these things. So this is the same as B dot C cross A. And you can also write one more if you like, and that's the same as C dot A cross B. So these are known as the cyclical properties of the triple scalar product, also known as the associative property. We're just going to use the first one. All right, let's write down the quantity known as h squared. So because I'm bringing B outside, that becomes R dot C, which is this. So that's dr by dt cross H. But look at our newly minted quantity. A is equal to dr by dt cross H minus kr over r. Therefore, dr by dt cross H is the same as A plus kr over r, because all I'm doing is taking this to the left side to get that. Let me substitute. So I get r dot A plus kr over r. Expand the dot product. So that's just r dot A plus k r dot r, which is r squared over r. So that's just kr. Now that gives me h squared equals r dot A, which is ra cosine theta plus kr. So here we have a interesting geometrical interpretation pop up. Let's continue drawing our orbital plane. This is our area vector A prime, and sadly I can't draw the Hermann vector because it's twice the size of the area vector and it'll get too big, so I won't draw it. Meanwhile, because so the direction, I told you the direction. The Hermann vector is going to be in this. Let me just lightly draw the Hermann vector so that you don't lose sight of it. That's h over there. And the velocity vector is what we had. That's the radius vector r. And the velocity vector is tangent to the orbit itself. So that's your velocity vector. Now, observe the direction of A. What can it be? I have the velocity vector across the Hermann. So V, if I transfer the velocity vector over here, it looks like this. It's still in the plane of the orbit. So V cross A is going to be in the plane itself. So one big motivation for Bernoulli to discover the true meaning of the direction of A was that it's lying in the plane of the orbit. So it's saying something about the orbit. And this took 3 years for Bernoulli to work out, which I'll lay out in the next 5 minutes. History is so ironical. What took people years to work out will just take me minutes to describe. That's your theta. Now I'll show you that this A vector is actually what's called the apsidal or apsis vector. So we'll talk about that soon. So let me just write it. Since A dot H is equal to 0, this tells you that A must be perpendicular to H, or A is fixed in the orbit plane. And that's called the apsis. I'll describe more carefully what the apsis is in a couple minutes. So we are almost there, actually. This will give us the equation of the orbit. Let's divide both sides by everything that does not involve r. So let me massage this equation a little bit. I'll write it as h squared equals r times a cosine theta. Theta is the angle between a and r, plus k. Now I'll divide both sides by what multiplies r. So I get r equals h squared over a cosine theta plus k. I'll divide both numerator and denominator by k. You'll see why I do that. So I get h squared over k, and then I get 1 plus a over k cosine theta. Well, that looks awful lot like an ellipse, actually like a conic section. So I'm going to call this 1 plus epsilon cosine theta. Johann Bernoulli must have been so pleased to find this appearance for the equation of the orbit, because they knew enough geometry back then to realize that this was a conic section. Today, what we know in calculus, we have lost in geometry, so I need to describe these things carefully. P is known as the semi-lattice rectum. I kid you not. These are Latin words. And epsilon, which is a over k, is called the eccentricity. So we have a formula for the semi-lattice rectum, and that is P is equal to h squared over k. Now, there's a construction of the ellipse that I'm now going to outline. I won't give you the full details of how this construction comes about. I'll just give it various names. So here you have the major axis. I'm extending it. And the line perpendicular to major axis known as the directrix. And then the ellipse is constructed with respect to these two. So I'm going to draw my ellipse like that. I'm just more interested in labeling the parts and not drawing a pretty figure, so I didn't bother trying to be neat here. Now, the sun is at one focus. I will label that focus as F. The planet is somewhere here. All right. The radius vector at any given time is pointing from the planet to the sun. Let's imagine actually the planet to be over here. I want to use colors that show well. So let's imagine the planet to be here instead of there. So this is your r vector. That's your theta vector, theta angle. So that means our the Runge-Lenz vector must actually be pointing in this direction. So that was Bernoulli's great contribution. to tell you exactly where the Runge-Lenz vector is pointing. Now, meanwhile, by the very construction of the ellipse, the semi-major axis is A, and this distance from the center to the focus is A times epsilon. The distance from the position of the planet to the directrix is P over epsilon. That's how the construction is made. And, this is R over epsilon. I should have said R over epsilon, not P over epsilon. This distance from this line is known as the lattice rectum, and that's why the quantity P is known as the semi-lattice rectum, because P is this amount from the focus on either side you go, where it hits the ellipse is known as P. So this entire line is known as the lattice rectum. So there's a lattice rectum, there's a directrix, and you have that beautiful geometry. This distance between the closed end of the ellipse and the directrix is A times 1 minus epsilon over epsilon. So pick up any old book on conic sections, and you can understand the full details of how the directrix is related to the lattice rectum. I won't go into that. It's a little beyond the scope of this lecture. So theta equals 0 gives you the perihelion distance. Rp, which we saw last time, was A times 1 minus epsilon, and theta equals pi. That gives you the farthest distance, known as the aphelion distance, Ra, which is A times 1 plus epsilon. Now, what we're going to see now is how these two distances come about. So that's going to be our next aim in this video. Now, to do that, we have to find out what the real meaning of the term P. P is h squared over k, but since we don't know what h squared is, that doesn't help us much. But this distance is P over epsilon. Let's try to break that distance up. So P over epsilon must be equal to this distance, which is given to us. It's A times 1 minus epsilon over epsilon, plus this distance. Now, what is that distance? It must be A minus A epsilon. So it's A times 1 minus epsilon. From this, we can easily work out what P is. So I get P over epsilon equals A times 1 minus epsilon is common to both terms, and then I just have 1 over epsilon plus 1. Well, that is A times 1 minus epsilon times epsilon plus 1 divided by epsilon. Cancel out epsilon from both sides, here and here. So I get P equals A times 1 minus epsilon squared. So indeed, that's how you get those two values. So let's write the R equation again in terms of the new understanding of what P is. So the R equation, R of theta, is P, which is A times 1 minus epsilon squared divided by 1 plus epsilon cosine theta. And now it's abundantly clear that when theta equals 0, we can work it out. R of 0 is A times 1 minus epsilon squared divided by 1 plus epsilon, and that's going to be 1 minus epsilon squared is just 1 minus epsilon times 1 plus epsilon. And that's just the perihelion distance, Rp. And when theta equals pi, I end up getting R of pi is A times 1 minus epsilon squared over 1 minus epsilon, since cosine of pi is -1. And this time the 1 minus epsilon cancels out, leaving us with A times 1 plus epsilon, and that's the aphelion distance, Ra. Now there's a name for the theta. It's known as a true anomaly. I believe I introduced this term last time also. It's an angle between the perihelion and the radius vector. And the major axis, which is this line I drew here, is called the apsidal line, or the apsis. So these are just astronomy terms. That's why in the ancient literature, they say that the Runge-Lenz vector points along the apsis. Now, furthermore, look at this meaning of eccentricity. The meaning of eccentricity is that the area vector is proportional to the eccentricity. The Runge-Lenz vector is. So let me write down what epsilon is. Epsilon is A over K, which means that A is K epsilon. And K, our understanding of K comes from the very beginning. It's G Newton times the total mass. So that's just G Newton times mass epsilon. So the Runge-Lenz vector's magnitude is proportional to epsilon. So for a while, the Laplace-Runge-Lenz vector was called the eccentricity vector for this reason. All right, so this is the state of affairs that was there until Bernoulli. Now there's another actor known as Hamilton. He comes along and talks about the energy of the Kepler problem. And this leads to one of the most beautiful interpretations ever of the two-body problem. So let's turn to that next. So this is Hamilton's contribution in 1845. So we classify the energy in terms of whether the orbits are elliptical, parabolic, or hyperbolic. So let's first of all define a specific energy. And in this case, it's the energy per unit reduced mass. So I'm going to call the specific energy E prime, which is the total energy E divided by the reduced mass mu. All right. Now Hamilton was interested in finding out the magnitude of the Runge-Lenz vector. So to aid us in that, let's work out A squared, which is A dot A. Well, we know what A is. It is given by that. So A dot A is just going to be that vector dotted with itself. So it's dr by dt cross H minus K R over R dot same thing. This is not as horrible as it looks. In fact, the computation will turn out to be pretty straightforward, actually. So let's proceed to do it. Now, just to aid me in not becoming cross-eyed, I'm going to call this the vector C for a little bit. Okay, then this becomes A squared equals dr by dt plus cross H dot C. And then I'll look at this term. That's going to give me plus K squared R dot R, which is R squared, over R squared, because I have to also multiply the two R's in the denominator. And then I'm going to get two identical terms, this dotted with that and that dotted with this. Since the dot product is commutative, I can write this as negative 2K R over R dot dr by dt cross H. Okay. Now I can use the associativity of the triple scalar product. So instead of, I can replace the cross and the dots. I can interchange the cross and the dots. That's what it really means. So I have dr by dt dot h cross c. But remember, c was all of this. So now I'll put back what c is. So that's dr by dt cross h. And then here I just have plus k squared minus same thing. I'll not mess with this for some time. Let's worry about this. That's your triple cross product. So we're going to use the same rule that we had, which is middle times the dot product of the outer minus third dot product of these two. So let's try that. dr by dt dot middle, which is dr by dt, multiplied by the dot product of h and h, which is just h squared, minus the other one times the dot product of these two things, just h cross dr by dt. Now h is perpendicular to the orbit plane and dr by dt is in the orbit plane, so it's 0. If you want to be more pedantic about things, you can just write down what h is. H is r cross dr by dt. So the h vector must be perpendicular to both r and dr by dt. So h cross dr by dt must be 0. So whichever way you look at it, this term makes no contribution. And then I have the remaining two terms, which won't be changed. All right, now let's look at this. If I have the same vector twice dotted, it's just the magnitude squared. So that's just dr by dt squared, h squared, plus k squared minus 2k. And at this point, I want you to, I'm going to write this as 2k over r times r dot. Here, what I'll do is I'll use the triple scalar product associativity again. So I'll replace this dot with cross and that cross with dot. So I'm going to get r cross dr by dt. And the whole thing dotted with h. Very convenient. I've written the h right up there, so I'm going to get an h dot h, which is h squared. So this is going to be, this is just a square of the velocity, so it's v squared h squared plus k squared minus 2k over r h squared. Now we'll differentiate both sides with respect to time. Well, the Laplace-Runge-Lenz vector does not is a constant. It keeps pointing in the apsidal direction without changing. So if I differentiate that with respect to time, I get 0. So on this side, what do I get? Well, I get derivative of two terms, but the h term makes no contribution since the Hermann vector is a constant too. So I'm just going to get d by dt of v squared times h, and then a big 0 from here, the differentiation of h squared and differentiation of k squared. And then here, I only differentiate the 1 over r term, which is about the only thing that's changing with time since the orbit is not circular in general. So that's a great point to come to, because now we essentially see that energy is conserved. So that's the big point of this exercise. So this gives me 0 equals, I'll divide both sides by h. So that, actually there's h squared here, sorry. I'll divide both sides by h squared. So I'm going to get, this is equal to d by dt. Also, I'll divide both sides by 2. Why not? So I get half v squared minus k over r, and that's equal to 0. Well, this quantity here is just a specific energy of the particle, because the total energy is 1/2 mu v squared minus k mu over r. So this is a specific energy. So this is E over mu, also known as E prime by our earlier definition. So we have proved this beautiful result, E prime, which is 1/2, I'll write this as 1/2 taken common between v squared, and then I'll write this as 2k over r. Well, what this gives us, the specific energy can now be solved for velocity. So we're going to solve for velocity. So I'm going to get v squared equals 2e prime plus 2k over r. Now let's go back to a squared. So the whole point of this exercise was to figure out what the square of the velocity is. Now that we know it, let's go to a squared to find out what it is. A squared is v squared h squared plus k squared minus, I'm just copying this down, 2k over r h squared, and now I'll substitute for v squared. So that's 2e prime plus 2k over r h squared plus k squared minus 2k over r h squared. Well, observe this minor miracle. This term and this term cancel out. So I have 2e prime h squared plus k squared is equal to a squared. Now the eccentricity epsilon is a over k. A is the square root of all this. So that's going to be the square root of 2e prime h squared plus k squared over k. And let me divide in and put this term first. So I get 1 plus 2e prime h squared over k squared. And now we can classify the three orbit types. So important moment in the history of the subject, seen from the viewpoint of the Runge-Lenz vector. Orbits are classified into types based on the value of epsilon. If epsilon is less than 1, then the energy E prime must be less than 0. Why is that? Because epsilon is 1 plus stuff. The only way that epsilon can be less than 1 is if E prime is less than 0. Well, if that is the case, you can actually show that epsilon lies between 0 and 1 for obvious reasons, because epsilon must be always positive and less than 1, and you have an elliptical bound orbit. So these are the orbits that we're familiar with, stars and satellites and so forth. If epsilon is equal to 1, the only way for that to happen, because it's 1 plus stuff, is for stuff to become 0. This is E prime equals 0. And that corresponds to a parabolic escape orbit. These are sometimes also called scattering orbits, because it corresponds to the least energy required for scattering with a certain impact parameter. And lastly, epsilon bigger than 1. The only way for epsilon to be bigger than 1 is if this quantity is bigger than 0, or E prime must be bigger than 0. These lead to hyperbolic orbits. So we have classified the orbit types. Now, from my point of view, the most beautiful aspect of this entire subject is the geometric interpretation it gives for an elliptical orbit. So let's look at that in some detail. So I'm going to go back to the semi-lattice rectum. For some reason, I enjoy saying that. It's such a quaint term. Sounds vaguely biological. So P equals A times 1 minus epsilon squared. That is the definition of the semi-lattice rectum P. Now P is also equal to h squared upon K. So we're going to put these two meanings of the term P together. So we got this P equals A times 1 minus epsilon squared, but we also have P equals h squared over K. We have not explored what happens when we set those two things equal to each other. Now we'll do that. So I'm going to set them equal to each other. What do I get? H squared over K equals A times 1 minus epsilon squared. Well, epsilon, meanwhile, is this. So I'm going to actually, 1 minus epsilon squared is just directly given by the negative of that quantity. So I'll write that directly. A times negative 2e prime h squared over k squared. Now, I can cancel out the h squared in both sides and one factor of k from both sides, and I end up with a equals negative k over 2e prime. Let's recall what k is. G Newton m is k, and that is G m1 plus m2. So let's also write down what the total energy is. E prime, specific energy, is 1/2 v squared. It comes from here. And I'll take this 1/2 back inside. 1/2 e squared minus k over r. And E prime, by this reckoning, E prime is also equal to negative k over 2a. What a beautiful equation. I'm going to get 1/2 v squared equals k over r minus k over 2a. And now comes this outstanding geometric interpretation, and that is the gain in kinetic energy is equal to the loss in gravitational potential energy going from r equals 2a to r equals r, i.e. the orbit. So this gives a completely different interpretation for the Kepler problem. Let's draw a circle of radius 2a first. I didn't want to take any chances, so I brought my compass along. So that's a circle of radius 2a, which means that that's 2a, the diameter is 4a, all right? So the ellipse has got a total length of 2a itself, and the focus of the ellipse is going to be here. So I have to make sure that I take as much from here as I give on this side. So this time I'm actually being a slightly more careful artist than I was earlier. There. So our sun is at the focus F, and the planet is going to be going around like this. Well, this interpretation says that what is the kinetic energy at any given point? The kinetic energy at any given point can be found as follows. You draw a straight line from the planet's position all the way up to this big circle of radius r. Drop the particle from rest from there up to here. The speed with which it's going when it hits this ellipse is the same as the speed that's tangential to the orbit. Just an amazing interpretation. So this speed here, this blue arrow here, is the same as the tangent blue arrow there. And you can do this any other point. So if I go here, I can extend this, back extend this. drop the particle from there. Obviously, it's going to be going slower because there's less of a drop. So the blue arrow is going to be smaller, and so this is going to be going slower. Where's the slowest speed? Obviously, where the drop is the smallest, and that's the smallest drop. So it's going to be the slowest downward speed, and that also is the slowest tangential speed. The highest speed is naturally over there because it's got the maximum distance to drop. That's going to be the maximum speed of the planet. Coincidentally, the maximum speed in the northern hemisphere occurs in the winter months. Okay, so we're actually less closest to the sun in the winter and farthest from the sun in the summer. The seasons are not caused by the distance, they're caused by the tilt, as you all very well know. And whatever works out for this side is also true for this side. I'd like to spend some minutes talking about one of my favorite books of all time, and that is this great American Mathematical Society publication called Variations on a Theme by Kepler, by two differential geometers, Victor Guillemin and Shlomo Sternberg. They are experts in their field of differential geometry, and so they take a look at the role of symmetries, especially Lie groups and symplectic geometry. So what Laplace, Runge, Lenz, and Hermann discovered was this deep symmetry. Now, if you know some group theory, you can follow some of the stuff they say here, but it starts out with very little background assumed. So if you know a little bit of differential geometry, you can actually follow a fair bit of this book. I'll just start from where he talks about Lenz and Runge. So you have the Runge-Lenz vector, its properties using Poisson brackets. Poisson brackets are things we'll talk about in a later video. We have not gotten there yet. When I talk about canonical transformations, I'll also introduce Poisson brackets. But right now, I just want to show you the importance of the Runge-Lenz vector historically. There was a good deal of wonder amongst the community at that time why the inverse square law was so special. And the inverse square law can actually be deduced. This is called the Newton problem. The Newton problem is, given the ellipse, can you deduce the inverse square law? So you can actually deduce the inverse square law using the Runge-Lenz vector, and you get the answer. It's going to be C over R. So the Kepler motion, the 1 over R type potential, is a consequence of the additional symmetry imposed by the Runge-Lenz vector. He calls the Runge-Lenz vector F. So, and he mentions why the inverse square law of attraction was a burning question in the 17th and 18th centuries. Many different answers were offered, but perhaps the above derivation would not have been very convincing then, or is not even now, but at least it's different. So I like their humor. Now, much of the derivations here are similar to what we did, except they look a little more concise. So L dot F equal to 0 tells you that it lies in the plane of motion. That's similar to our Hermann vector dot R equals 0, told us the same thing. And he gets the equation of the orbit, which is a conic section, by similar methods. The treatment here is a little bit more sophisticated. He also goes into Kepler's third law using scaling arguments. So I won't get into that. And then he goes off in new directions, quantum mechanics and so forth. Highly recommended book for those who have the time and the background.